So a plane is a slice, if you like, of space. And I like to think of it as almost like a piece of paper, that where a piece of paper has edges, we are thinking with no edges, but that occupies a kind of two-dimensional sort of space, slice, if you like. And here I have obviously confined it to a sort of piece of paper floating in the air, but I think that's one of the easiest ways of modelling it. So much like when you draw a 3D vector, you don't draw it coming off of your page. If you could somehow do that, you confine it to the paper in front of you. In the same way here, I've drawn a plane as a small rectangle at some angle in space. Now, we need to describe the equation of the plane. There are multiple ways of doing this, but we'll kind of build up through those ones. So the first one is, well, let's pin it in space. Let's decide where, relative to our origin O, this plane is. And we can do that by selecting a point on the plane that we know is there and using the position vector OA as our locking it in space. So our plane, which we will use pi to describe, so pi is, for a start, the vector A. That gets us from the origin to a fixed point on the plane. How do I describe the rest of the plane? Well, one way of doing that is to think about how you would move around the plane when you start at A. And the minimum amount we could say is that we need two other vectors that help us move around the plane. And then we could do any set of multiples of those two vectors, but as long as they have different orientations, we can get to any other point on that plane. So if we call this vector B and vector C, then our plane is, well, we'll use A to get to it, and then we will use any multiple of B that I need and any multiple of C that I need to move around the plane. And because this would then get me to any point on the plane, it is an equation for the plane. So the plane is described as vector A plus lambda B plus mu C. Now, as long as B and C are not parallel and they are not 0, we will be fine. So B and C are non-parallel, because if they're parallel, they're the same vector in a sense. They need to have two different orientations and non-zero, so they actually have a quantity and will actually move us around vectors. Hopefully that's a fairly intuitive way. Now, one thing we want to be able to do is create a Cartesian equation, because we like our x, y's and z, let's be honest. And if I start to try and do that with this equation, I'm going to run into some serious trouble, because I'm going to have an awful lot of unknowns and variables and things going on. So that must mean we've got more that we can do to describe the plane in terms of a vector. And hopefully then, if we can get another equation in terms of vectors, that might be more helpful for us in creating a Cartesian equation. So the other thing that remains constant in a plane, because it is this sort of slice of space, is that on that plane there will be a normal vector that is the same the whole way across that plane. Otherwise it wouldn't be a plane, it would be some other surface that had some curvature to it. If it is a plane, it's that flat piece of paper orientated in space somewhere. And so there must be a normal vector that is true for the whole plane. So, I mean, we can just pop it in somewhere, but that is going to be normal to the plane all the way across the plane. And that's normally something that we can define quite quickly, or we will be given. So that's really useful. Now we've just got to create an equation out of it. So we still need to pin our plane in space. So I'm going to select a point A, and I'm going to use the vector OA, the position vector, to lock my plane in a particular bit of space. I'm going to pick a generic point R, something that's on the plane and could be anywhere on the plane. and therefore would be any point on the plane and can help us describe it. And we're going to find the vector AR. So the vector AR, that's our vector R, which would be the position vector of R relative to the origin, that's fine, minus A, and that's all good. That's fine, and that could be literally anywhere in the plane. It could be over here, or down over here, or right on the edge of it, who knows. What we do know is that that vector AR lies completely in the plane. There's no part of it that sticks out or anything like that, and therefore it must be perpendicular to our normal vector n. We know that AR must be perpendicular to our normal vector because it lies in the plane, it's part of the plane, and we said that the normal was perpendicular everywhere on the plane. So we've now got the dot product between these two vectors equaling 0. It's one of the lovely features about perpendicular vectors. I'm going to just chuck some other stuff in here. I'm going to replace AR with the R minus A that we had calculated before. And then the dot product will allow us to expand this to R dot n minus A dot n. If you're not entirely convinced by that, I'll just try and get my dots and my minuses the right way around. Do pause the video, chuck some numbers in here, and just convince yourself once that you're happy numerically with it. Now that is not, of course, a proof, but it might give you a sense of how a proof would work for this. But do chuck some numbers in, convince yourself that you're happy that that's true, and if you want to, go ahead and prove it formally. So we've got R dot n minus A dot n equaling 0. Now, A is a fixed point on the plane, we know it. N is the fixed normal to the plane, we know it. And so A dot n will produce a value. Don't forget the dot product is also called the scalar product because it takes two vectors and does something to it to collapse them down onto a number. I can replace that with the letter K to represent a constant, something along those lines. So I end up with R, which is a generic point on the line, I don't know it, dot n, minus the dot product between two vectors I do know, hence they're a number, that the dot product ends up on a number, equaling 0. And we get this equation, that pi is R dot n equals K. Pi, of course, being our plane, not proper pi, and it is the dot product between the generic vector in the plane, your normal, and equal to a very specific value of K, which is A dot n. Okay, so this new equation that we just derived a minute ago is way more helpful for finding a Cartesian equation. Now, I've said that R could be anywhere, it's a generic point on the plane, so we're going to call it x, y, z. And the reason for that is so that it can be anywhere on the plane, but also this generic x, y, z is going to help us create a Cartesian equation. I also said that n was the normal to the plane and it is known. It's a known normal. So we're going to give it the letters A, B, C to represent numbers that we could put in very easily and that we know quite a lot. And then we're going to put this information into that equation that we just derived a second ago. So we're going to give ourselves R, x, y, z, dot n, a, b, c, and that's going to equal our number k, which again we could calculate if we have our point A and our point N. But we're trying to get a general formula here, so we're just going to go with as general as possible. The dot product then would be AX plus BY plus CZ, and that equals K. And notice all my vectors have disappeared, and what I'm left with, in fact, is a Cartesian equation, X, Y, and Z. So this is the Cartesian equation to a plane.